Greetings, ladies and gentlemen. Welcome to Chapter 15. Chapter 15 is called Organometallics Chemistry. As its name implies, we're talking about organic molecules that also have metals in them. The three examples are organolithiums, in this case, 1, 2, 3, 4, butyl lithium. Doesn't look like it follows the traditional rules of nomenclature, does it? No. Cation, anion, it's just like out the window. It's okay. We got to live with it. Organolithiums followed by what's called a Grignard reagent. In this case, butyl magnesium bromide. Remember, magnesium is a 2+ cation. So when we look at the equivalence of these things, you should think of magnesium as 2+, the Br is 1-, and the carbon is the other minus. We'll get back to that. The last one is called a Gilman reagent. And this is dibutyl copper lithium. And like I said, when you're thinking of, back in the day, we used to cross off spectator ions, right? That doesn't change. You can think of the butyl lithium as the equivalent of, almost the equivalent of is what that means. A carbon with a minus and a lithium with a plus. And just for old time's sake, remember what we used to do with those? We used to cross them off and pretend they weren't there. Right? Similarly, with a Grignard reagent, you've got your same butyl minus, and the other spectator is this complex ion, MgBr, with a plus. It's like magnesium has a 2+ charge. Only one of those is balanced with a Br, the other's left over. And that makes that also a spectator. It's not used to spectators like that. And the Gilman, I'm not gonna say it's the same. It doesn't really behave like a carbon anion, a traditional carbon anion. It does other things. So, cut to the chase. Very important for you to know right away. Whatever we do with a butyl lithium, an organolithium, you can do the same chemistry with a Grignard reagent. These behave the same chemically in this class. I am going to write that in the box. These behave the same chemically. So when we talk about activity 2 and maybe 3, where we're using these things, they are interchangeable. Okay? And the Gilman has its own unique chemistry that is not interchangeable with the other two. So we need to know how to make these things. Very important. That's what this document's all about, really. We haven't done any of the activity yet. I mean, if you wrote all that down, that's great. You should. Just good process it for your mind. How do you make an alcohol into an alkyl bromide with the same carbons? Don't say HBr. I mean, in this case, it's the one time it'll work, but I don't like it because there's so many times it doesn't work. PBr3 is the safe one you should use every time. PBr3. And that was a chapter 10 review. And now the new stuff. This is chapter 15 here. Chapter 15. You want to make an organolithium from alkyl halide. This has to be an alkyl halide or you can't do this reaction. Can't do it from the alcohol? Nope. That's why we had to make the alcohol into this first. Lithium metal. Lithium metal. Put it red. And hexane is a very common solvent. Solvent choice is important with organometallics. We'll talk about that in one of our activities after this one. So what happens to the lithium? It goes from being a metal, which has no charge, to being clearly lithium plus. What do you call that reaction? When a metal becomes a cation. It's always the same type of reaction. Oxidation. Therefore, and for that reason, what happened to the carbon? When it went from a carbon that was just a little bit negative, a little bit positive. Oops. Why am I saying it's a little positive? Because bromine's more electronegative, yeah. And now, look, you took something that was plus and you made it into a full minus. Yeah, that's a total change in character, isn't it? All right. And what do you call that reaction when you gain electrons and you become an anion? Reduction. That's a reduction. So carbon got reduced, the metal got oxidized. Long story short, it's redox. Yeah. Same for the next one. Magnesium metal. And if you try hexane, you get no reaction. Trust me. Yeah. This one's very picky about the solvent. The solvent needs to be an ether. And just go ahead and use the most common ether. Which one's that? Do you know offhand? Diethyl ether. And my Orgo 2 lab students will know that by the end of the semester. We will have used diethyl ether about 10 times. And diethyl ether looks like this. There you go. And the Gilman, it's a two-step process. In fact, what I should have done was drawn an arrow from the organolithium to the Gilman, because the first step is to make the organolithium. So you're going to have the product that's listed up here first, right here. And then two, you have to convert it to a Gilman by using copper +1 iodide. And I do want to point out down here that it is copper +1 and it's lithium plus, right? And it's two of these. If you're talking about charges, there's your ions that this breaks down to. I'm not going to put a roughly equal to sign because it doesn't behave like an anion. But if you're looking at, balancing charges, etc., you got a copper +1 lithium +1, and 2 carbons that are minus. So copper didn't change its oxidation, did it? Copper was +1 in the beginning, copper's +1 at the end. This is not about redox. The redox was in step 1. This is just about exchanging lithium for copper, the second step. Okay? That's how you make Gilman. And I want to do just, this video is almost over. Quick reminder that you already knew about an organometallic compound. We just didn't call it that back in chapter 7. So I'd like to have a review as much as possible. If you're lucky, what you can do is take this guy and just do something like KH, and you have this. Right? I mean, it's an organometallic. Potassium's a metal, right? This is an acetylide. An acetylide. And this is what kind of reaction? Here's the reminder. The other product is H2. You can connect partners in this one, right? Calculate an equilibrium constant in this one, because it's what kind of reaction? Uh-oh, worried here. I can connect partners in this reaction. It's an acid-base reaction. So really, chapter 7 combined with chapter 4, isn't it? We used it in chapter 7 as a nucleophile. Chapter 4, we actually, it's the first time we learned how to make it. It's just acid-base. And we'll just separate that out and call that a video. Oh, I didn't save it yet. I'll come back to that.